Okay, so good morning, everyone. Um, Welcome to the joint CATS TAL Symposium, Charting the Future of Urban Mobility. For those who don't know me, my name is Amr Shalabi. I'm a professor in the Department of Civil and Mineral Engineering at the University of Toronto. I also serve as the director of the Transit Analytics Lab and co-director of the Center for Automated and Transformative Transportation Systems, along with my colleague, Professor Bahar Abdelhai. First, before we start this event, I would like to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently the Mississaugas of the Credit River. So today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Um, this year, we're actually having two events in one symposium. As many of you may recall, that every year both the Transit Analytics Lab and the Center for Automated and Transformative Transportation Systems, CATS, hold their own research day or symposium, um, essentially to showcase their research advances, discuss emerging transportation problems and topics. This year, we decided to hold the two events jointly, today and tomorrow, to share our most recent research activities and endeavors, and also have a chance to engage the wider community to get some feedback uh, and have some conversation about uh, critical and emerging transportation topics. We also have we are honored to have two guest speakers, one today and one tomorrow, that will address critical transportation and transit topics. CATS really held six previous symposia in the past 6 years. This is going to be their seventh. TAL had three research days previously, also in addition to a number of workshops and symposia on as needed basis. So today will be really focused on TAL research activities, Transit Analytics Lab. So I'm just going to spend a couple of minutes just to remind everyone what TAL is all about, and also talk a little bit about what to expect today. So TAL was created in 2020, essentially to bring together transit and data science researchers, also technology specialists, transit agency and public sector practitioners, as well as consultants, bring them all together in a common forum to promote transit decision making using data analytics. So the main focus really of TAL is to really enhance decision making in the transit industry, in the transit space, using diverse data sources and advanced analytics. This is really the main focus. The two main objectives of TAL is obviously to foster innovations in data-driven transit analytics, and you will see a few of those examples today, as well as training students and as well as practitioners in advanced transit data analytics. TAL has been quite successful over the past 3 years to host, train, and graduate a number of students at all levels, PhD, master's, and undergrad, as well as postdocs in different transit data analytics, tackling different topics. And one core activity really of TAL is this event here and other events that really aim to transfer whatever knowledge and technology that we produce within TAL to share it with the wider community, both the academic community and the practitioners. So we've been actually quite diligent doing this over the past few years. We've held TAL has held about maybe 7 workshops in total. We also engage in the development of standards and integration models. So what do you expect for the remainder of the day? So we're having a full day, rich with a lot of activities, a lot of talks, as well as a guest speaker. So each one of the talks really will be a combination of some technical aspect or technological aspect, such as, tackling on-demand transit or electrification, or some critical service planning topic, and so on and so forth, and tackling those topics using advanced analytics. And those methods could be optimization methods, simulation, AI, machine learning, reinforcement learning, and deep learning, as well as large language models. So you will see in the different talks different kinds of methods that we've implemented, and you will also see different kinds of data that we've used to tackle the uh, transit topics that we have been aiming for, and using the methods that we developed. So you'll see different kinds of data that we've been using, AVL and APC, press to card data, or AFC, automated fare collection, as well as not very traditional data sources like Wi-Fi, social media, trip planning data, and as well as more traditional transit data sources such as household travel surveys and rider satisfaction surveys and so on. So each one of the talks will really be a combination of those. Um, just very quickly to have a look at the program. So just following this short introduction, we're going to have a session. Each session is going to be hour and a half, consisting of four presentations. And each presentation will be 15 minutes, followed by 5 minutes Q&A. So if you have any questions, please write those questions in the chat box. So this is the only way of communicating your questions or comments if you wish. We will really endeavor to answer those questions in the Q&A portion. If we don't really have sufficient time, the speaker will perhaps respond in the chat box itself to some of the questions. So we're featuring today three sessions. Each one is an hour and a half, consisting of four presentations. The first will be on bus electrification and on-demand transit, um, tackling different aspects of those two technologies. Then we're going to have a break of 15 minutes. Following that, we're going to have another session on analytics that were developed at TAL to improve transit performance. Um, and following that, we'll have lunch break for about 1 hour. After the break, we're going to have our keynote speaker, Dr. Brandon Hemley, who's going to talk about really the transfer of um, transit analytics research outputs into practice, and really the challenges associated with that, and some of his perspectives to overcome some of those challenges. The last session of the day will start at 2:30 p.m. and it will tackle different topics. Uh, Understanding ridership trends post-COVID, also learning more about customer experience, and a very critical topic on capital transit projects, especially in our context here in Canada, and why is it that it costs a lot more than elsewhere in the world. So some neat results about this will be shared. Um, and the program will end at 4 p.m. Uh, Before we start, I just wanted to mention that there is so much really that we shared over the past few years, which you can find on our website. So I highly encourage everyone to visit our website, as well as we have a YouTube channel. So every workshop or research day in the past, or any presentation, you'll find a recording of that on our YouTube channel. So you can go back as far as 2020. One important event I would actually like, and we are proud to mention that in 2020, the very first year of TAL, we hosted the International Transit Data 2020. Both Dr. Brendan Hamily and I were co-chairs of this important event, which takes place every year. It brings together researchers and practitioners from around the world who are interested in transit data analytics. So in 2020, we hosted it in Toronto. Unfortunately, it was the year of of COVID, so it was online. The advantage of this is that we have recordings of all talks, which you can find on our YouTube channel. Um, uh, Also, I would like to acknowledge really all the sponsors and collaborators. Really, without their support, we can't achieve what we are going to share with you today. So TTC, MyWay, BAI Communications, Durham Region Transit, Metrolinx, and NSERC, as well as others, other partners and sponsors. And I would like also to take the chance at this point to say, the invitation is extended to everyone who would like to collaborate with TAL to reach out. That's really how it works. So you will see examples of those partnerships today. And if you have any pressing problem in your agency, we'll be very happy to talk to you and explore collaboration opportunities. So with this, I would like to then pivot to the first session. So I'm going to stop sharing here. And okay, so the first session will feature 4 presentations, as I mentioned. It will be focused more on electrification and on-demand transit. And we will share with you some new insights and tools. So the first presentation will be delivered by Dr. Karim Othman, who defended his PhD recently. So he's currently a postdoctoral fellow at the Transit Analytics Lab at U of T, and his research interests include public transit, electric buses, multimodal corridors, traffic management, and intelligent transportation systems. So Karim will talk to us about some of the work he did on bus fleet electrification, specifically energy consumption prediction and fleet sizing. So without further ado, Karim.
Great. Thank you, Professor Amr. Can you hear me?
Yes, we can hear you.
All right. Good morning, everyone. So today I will talk to you about the tools we have been developing here for bus fleet electrification. And I'll just quickly move to the second slide. We have 3 main goals, or we have 3 main tools. The first tool is actually focusing on predicting the energy consumption rate of electric buses. And then after that, we have the second tool, which is focusing on fleet sizing. So basically, you can use this tool to predict or to estimate the required number of electric buses you need to electrify a certain route. And finally, based on these tools, we have been working on a problem that really focus on which buses to electrify first. So basically, we are trying to predict the energy consumption rate, we are trying to predict the fleet size, and then we are trying to provide transit agencies with some guidelines on which routes to electrify first. So what was the motivation behind all of that? Usually bus manufacturers or electric bus manufacturers will provide you with the maximum bus range, which is actually estimated under certain conditions. However, in real life, there is really a wide range of factors that affect the energy consumption rate, such as the number of passengers on board, the number of intersections, the number of bus stops, and definitely the temperature is one of the main factors that really affect the energy consumption rate. So we really need some sort of prediction models that allow you or help you in the planning stage to understand the impact of these factors in the energy consumption rate and in turn in the bus range. So when we look at literature models, we have two types of models, either simulation models or real-world studies. So our research really here is focused on real-world studies, and we will use real-world data to build the prediction models. So we have been using data from the TTC. So the TTC fleet consists of 60 electric buses, 10 PYD buses, 25 New Flyer, and 25 Proterra buses. And these buses were deployed in 2019. And at that point, the TTC was the transit agency with the largest electric bus fleet in North America. And this was actually part of the TTC Green Bus program that targets 2037 to full transition to electric buses. And actually, the city of Toronto is targeting 2040 to full electrification using electric vehicles, electric scooters, and so on and so forth. So this actually emphasized the need for electric buses or for energy prediction models as we are moving rapidly toward this electric buses. So the TTC has been deploying these buses in 43 routes, and we have used the average energy consumption rates from 2019 to 2021 to build our prediction models, basically. So let's first start with the performance of the different bus types across the different seasons. So basically, we have New Flyer represented in blue here, Proterra in green, and then BYD in red. And then we have the energy consumption rate in kilowatt hour per kilometer in the y-axis here. And this first figure is showing the box plots for the entire data set. And this one is showing the box plots for the summer data. And then we have the data for the fall and spring, and then for the winter. And let's look at the summer, fall, and winter data. And when we look at New Flyer data, we will see that the energy consumption rate remains almost consistent across the different seasons. However, for Proterra and BYD, they remain consistent in the summer, fall, and spring. But when we look at the winter, there is a significant increase in the energy consumption rate. So basically, there is the different buses are actually behaving differently to the temperature change, with New Flyer really being the less sensitive to energy, the less sensitive to temperature change. Around 50% of the energy consumption is actually ranged between 1.2 kilowatt hour per kilometer to 1.4 kilowatt hour per kilometer. And really the main factors that really contribute to this difference is actually the heating system, because New Flyer buses are actually using diesel auxiliary heaters, while Proterra and BYD are using their batteries to heat the bus in the winter. So let's start with the first tool, the energy consumption prediction tool. So in order to build this model, we have been using a number of factors, starting from vehicular features or vehicular variables, operational variables, route variables, and external variables. And when we build this prediction model, we have made sure that typical values are really actually known in the planning stage. So you can use these values to really predict the energy consumption rate at the planning stage. So just very quickly, I will not really get into much details because I presented the energy consumption rate part last year in the TAL Research Day. So I will just very quickly show the SHAP analysis. So the SHAP has been used for model interpretation and to really understand the impact of the different inputs in the energy consumption rate. And this is the main result. This is the average temperatures. And the results really have shown that the main factor contribute or affect the energy consumption rate is the average temperature. And then we have season 2, which is actually the winter. So basically, this data is telling us that the average temperature has an inverse relation with the energy consumption rate. So increasing the energy will result, increasing the temperature will result in lower energy consumption rate. And actually, you have higher energy consumption rates in the winter. So basically, seasonal data are actually the main factor affecting the energy consumption rate. So in terms of conclusions, so basically we have seen that the energy consumption rate varies significantly for every from one bus type to the other, and we have seen that while some buses are actually highly sensitive to temperature changes, some of these buses are not really sensitive, and the heating system is really a major factor that affects the energy consumption rate. And finally, temperature-related variables are the main variables affecting the energy consumption rate. All right, so now let's move to the second part, which is the e-bus fleet sizing problem. So basically here we are trying to estimate the required bus fleet size in case of electrification. So basically, what is the main issue? The main issue is that the transition to electrification is actually challenging because you have limited bus range, which was not an issue for diesel engine buses. And there is a very common term, which is range anxiety, that's used really by transit agencies, that they are really not sure about the range of their buses and when the bus will be out of service or need recharging. For example, in the city of Toronto, we are following an overnight depot charging. So we used our data set to really understand the impact of electrification on the required bus fleet size. For example, if you have a certain route and this route is currently served by 10 diesel engine buses, how many buses do you need to serve or to offer the exact same service? So basically, we have used the TTC data set and we have estimated the required fleet size. So it's based on two main points, which is actually you need to serve the big demand, very similar to what we actually follows when you estimate the required fleet size for diesel buses. So basically, you estimate the frequency. It's usually function or you divide the passenger loading in the maximum loading section divided by the vehicle capacity, and then it's multiplied by a number of factors. But basically, the frequency is the passenger loading in the maximum loading section dividing by the offered capacity. And then you can estimate the headway, and then the number of transit unit is basically the cycle time divided by the headway. In the case of electric buses, you have an energy limitation. So you need to estimate a new fleet size based on the energy requirements. So basically, you estimate the energy required per cycle. So basically, you have the length of the cycle, and you have the average energy consumption per kilometer. Then you multiply the length of your route, or the cycle length, you multiply it by the average energy consumption rate, you get the energy consumed per cycle. And then based on it, you can estimate the number of cycles that can be completed by bus in one fully charge. So basically, you have the battery capacity, and then you divide it by the energy needed for one cycle, for the bus to complete one cycle. And then usually transit agencies do not really consume the entire battery capacity. They usually use around 80 to 90% of the capacity. So we multiply the capacity by 0.85. And finally, you can estimate the number of transit units or the number of buses needed by dividing the total number of cycles completed by the entire fleet in one day by the total number of cycles that one bus can complete. And this will give you the required number of buses to actually overcome the energy limitation. And at the end, your required fleet size will be the maximum of the two values, the one using the one actually estimated to serve the big demand, and the one is actually estimated to overcome the energy limitation. And again, we have calculated this number for the different bus routes we have, and we have estimated it even for different seasons. So basically, after that, what we try to estimate is we try to use this equation, which is actually telling us that we have the number of transit units for electric buses equals to beta 1 multiplied by the number of transit units. So basically, we try to estimate beta 1. So we try to estimate a ratio. This ratio is actually dividing the number of transit units needed for electric buses divided by the number of transit units using diesel engine buses. So it's actually called the replacement factor. So it's a number you multiply it by the current diesel fleet to estimate the required electric fleet requirements. Yeah, and this is actually the relation between the two values. So in the x-axis, we have the diesel fleet size, and in the y-axis, we have the electric fleet size. And this is the data points we have. And we have seen that your required electric bus fleet is actually around 1.34 the existing diesel fleet size. So if you decided to replace a certain route, you will need 34% increase in your fleet size. So if you currently serve one route with 10 with 10 diesel engine buses, you will need 13.4, which is actually 14 electric buses. So this is our replacement factor. But this is actually was done generally. But we have seen that the energy consumption varies from one season to the other, and it also varies from one bus type to the other, and the different buses have different capacities. So we have estimated beta 1 for the different bus types across different seasons. And this figure is actually showing the results. So we have the replacement factors for BYD buses, Proterra, and New Flyer, and the blue bar here is showing the summer data, the green one is showing the fall data, and the final one here really here is showing the winter data. And we can see that the replacement factor required varies from one season to the other. So for BYD, the replacement factor is around 1.25 or 1.3 in the summer, while this jumps to 1.3 to 1.35 in the fall, and then in the winter it increases significantly to 1.8. So we can see really a big difference between the fleet size requirements from one season to the other. And this actually tells us that if you decided to electrify a certain route based on the winter data, part of your additional fleet will remain idle in the summer and fall. So basically, if you decided that if you currently serve a route with 10 diesel engine buses and you decided to increase it or multiply it by 1.8, so you will have 18 electric buses, basically a big portion of this fleet will actually remain idle in the summer and fall. The same actually can be observed for Portera, but the impact of the seasonality is actually slightly lower, and the same for New Flyer. But New Flyer is actually the most consistent and the one that has actually the least percentage of idle fleet moving from one season to the other. Right. So basically, we have seen that on average, if you decided to electrify a certain route, you need to increase your fleet size by 35%. And this requirement actually varies from one bus type to the other and based on the season. And also the percentage of idle fleet in the summer varies depending on the bus type and the heating system adapted. All right, so finally, the final question is, which bus routes to electrify first? So basically, what we have done here is that we have classified our routes into routes that has replacement factors equal to 1 or replacement factors higher to 1. So basically, replacement factors equals to 1, it means that you will need any increase in the fleet size, but if your replacement factor is higher than 1, it means that your route requires really fleet expansion. And then we compare the properties of the two categories and analyze them to understand really which routes achieve the lowest replacement factor. And the main goal is to find really the properties of the routes that achieve or have a replacement factor equal to 1, so that we can actually guide transit agencies to select these routes so that they can actually replace one diesel bus by one electric bus. So basically, for the comparison, we have used hypothesis testing and box plots. And for example, here we have the routes. We have two types of routes that does not require fleet expansions and routes that actually require fleet expansion. And then we have the distribution of the average bus speed in the y-axis here. And this figure is clearly showing us that if you do not really want any fleet expansion in your fleet, you need to select routes that has lower average operating speed. So if you selected routes with high operating speed, you basically will need to increase your fleet size. Secondly, for the route length, the same can be observed. If you want no fleet expansion, you will select routes with shorter route lengths. And we have basically done the same for the remaining factors. For example, for the headway, we have seen that there is no difference between the two scenarios, the no fleet expansion and the no fleet size. So basically, the headway is not a major factor that really affect your choice. And if we can carry on the number of stops for both directions. So this is actually telling us if you are selecting a bus route, you actually try to select the routes that minimize the number of bus stops in your route. Just very quickly, this is the results of the hypothesis testing for the remaining variables. I didn't really show all the results for all the variables, but basically the headway was not really the significant variable. So if you are deciding or selecting certain routes, do not decide based on the headway, but you can decide based on the remaining features. So basically, which routes to electrify, you need to select routes that has lower operating speed or low operating speed, shorter route lengths, lower number of intersections per kilometer, lower number of bus stops per kilometers, and finally, you need to select routes with low average daily ridership. And yeah, that concludes my presentations. I'll be happy to answer your questions.
Thank you very much, Karim. We have one question for you here. The question is the fleet sizing method also valid or usable with transit systems that use interlining?
Yeah, that's a good question. So so far we did not consider interlining. We are just dealing with one route, with routes isolated from the other routes. But the next step forward is to actually do interlining and to optimize the fleet for the entire network. So basically, you can share buses from different routes based on the energy consumption and the requirements. But yeah, so far we didn't really include interlining in our fleet sizing work.
Karim, there is a request to show the last slide again. If you can show the last slide.
Yeah. This one?
Yeah, yeah. So, yeah, maybe Shah, if you have further questions, you can ask them in the chat box. Brendan is asking, is topography a factor?
Yeah, so that's a good question. Like the main issue here is that in Toronto, basically most of the routes are actually flat, and even the 43 routes we have been really building the models based on are basically flat. We don't really have significant variation in the topography. So for our case, it is not a significant factor. But yeah, in literature studies, you will find that this is actually a significant factor. But for our case, it's not really a significant feature.
Karim, I have one question. Like you showed that there was one bus type, the performance and the fleet size requirements in the winter are way higher than in the summer. Can you just explain the difference between those different bus
Yeah, I
types?
think Yeah, so basically what contributes to this difference is two really main factors, right? Two main factors. The first is that BYD buses and Proterra are actually relying on their batteries to heat the bus. On the other hand, New Flyer is actually using diesel auxiliary heater, so it's not really sensitive to temperature change. On the other hand, Proterra and BYD are actually highly sensitive to temperature change. This is number one. Number two is actually the battery capacity. BYD has a very small battery capacity. The battery capacity is around 360 kilowatt hour. On the other hand, Proterra has significantly higher battery capacity. It's around 25% higher. It has around 25% higher capacity. It's around 440 kilowatt hour. On the other hand, New Flyer also has higher capacity than BYD buses. So if we added the impact of the seasonality and the impact of the battery capacity for BYD buses, you will see there is a significant increase in the fleet size requirements from moving from the summer to the winter.
Okay, very good. Well, thank you very much, Karim. So now we'll move to the second presentation. Actually, the next three presentations will be more focused on on-demand transit. So the first one will be focused on really the drivers of on-demand transit ridership. So it will be delivered by Ala Itani, who's a PhD candidate at the Department of Civil and Mineral Engineering, specializing in transportation. As a researcher, Ala focuses on transit planning and analytics, specifically integrating on-demand transit with conventional transit systems. Outside research, she enjoys being active, traveling, and trying local coffee shops. So if you have any recommendations for Ala for any good coffee shop, let her know. Ala, over to you.
Okay, can you see my screen?
Yes.
Let me see the presentation mode. It's good.
Yeah, go
Okay,
ahead.
awesome. Good morning, everyone. So today I'll be the first talking about some research we've been doing with on-demand transit. And it's specific to really understanding the spatial and temporal factors that affect on-demand transit ridership using real-world data from a region of Durham. So a little bit of introduction. I'm not going to spend so much time here. I know everyone is familiar with on-demand transit now. It's been really popular in the last few years. But the point that I want to make from this slide is that on-demand transit is not one thing. It really could serve different objectives, and it has multiple forms. It could have different stop configurations. It could be serving like first mile, last mile, having really more structured form, and it could be more random, less structured form. Like the door-to-door operations. The point that I want to make here is that we cannot compare on-demand transit to private ride-hailing companies because they really operate based on different objectives and different business models. On-demand transit is not to make profit, it's to fill gaps in the system, and that's what we will focus on. So the motivation behind this work really started with on-demand transit really being an emerging form of transit and growing all over the globe, but also in Canada. So if you see this map on the right, we see where on-demand transit is across Canada and what provinces and different cities. And a lot of these were pilot projects, but some of these were permanent services, like the region of Durham, like York region. And there's a lot to learn from these big agencies and big on-demand transit deployments. So for the planning part, the early on stages of on-demand transit was really based on judgment. There wasn't really a holistic view or like fixed planning guidelines in place towards what is a good practical implementation of on-demand transit. But with all the data that we have, with all the different case studies, there's a lot of lessons learned that we can kind of collect and to build better guiding principles. And one of those steps was really our interest to explore what a successful on-demand transit solution look like, what is the right size for a need, how it could be integrated with the broader transit network. And as part of this work, our focus on ridership prediction had really taken a lot of weight. So the objective of this part of our research that I'm going to be talking about today was really to examine and study one of the largest, it's not the largest, but one of the largest on-demand transit deployments in Canada and Ontario, which is the region of Durham. We were lucky to have great data sets from the region of Durham. We took this data set, we were trying to understand on-demand transit trip patterns, where people use it, when do they use it. And from this data, we were able to build different models to really highlight what are the significant factors that increase or decrease on-demand transit ridership, which includes the service zone itself characteristics, the socioeconomic characteristics, some fleet and other external factors. So just to begin with, I'd like to just spend a little bit of time talking about the regional municipality of Durham. So Durham is just east of Toronto. It's a big municipality it's a big region that has 8 different municipalities. We consider that municipalities of Pickering, Ajax, Whitby, and Oshawa in the southern parts of the region are more of an urban municipalities. And we can see from this graph that shows the population, the darker colors are higher population, lower colors, lower population. So we do see that those municipalities are more dense. These are more urban municipalities, whereas the rest of the municipalities in Durham, they're more really rural. They have less demand, they have less population. The nice thing about the on-demand transit in Durham is that it operates across the whole region, across the whole municipalities, but they do have different forms in different areas based on the need and based on the different characteristics of that area, which makes it a really good case study for our service zones, how these different service designs really affect on-demand transit ridership. On average, there's approximately 17 vehicles that serve the whole region across the whole day. That's specifically for on-demand transit. And the good thing is that I want to say is that the on-demand transit is fully integrated with the scheduled bus services. So they have free transfers between on-demand and fixed bus routes and vice versa. To move on, just to talk about the zones, on-demand transit in the region of Durham, within the time that we looked at, in between January 2022 and June 2023, they were operating at the service zone level. So it's not everywhere and anywhere, specifically in the urban zones. So we do see like pockets of areas where on-demand transit fills the gap, it replaces an underperforming bus routes and whatnot. On the other hand, we do see that during the day, we have more in the rural region, on-demand transit operates everywhere, basically. It has different operational modes in the rural region, but it's mostly door-to-door. And they also provide overnight services. And these, we call them the overnight zones, which we also include in our models. And these are overnight zones, they replace a lot of the fixed bus routes during the night hours where the demand is really low. Yeah, and these are the urban zones where we see that there are more pockets of service during the day. So the first thing we're interested in to see how this temporal variation across the week, across the time of the day, across the days of the week looks like for the rural kind of service zones and for the urban operations of on-demand transit. And we do see that we have for the rural on-demand transit, we do have a similar or a typical travel pattern. We have like a small morning peak, we have a higher afternoon peak, and we have a lower weekend demand for the on-demand transit. But the interesting part about the urban zones is that we really have very high demand in the overnight and early morning hours where the fixed bus routes is limited and on-demand transit replaces that mode. And we have a lower demand during the day because there's more fixed bus routes operating in those regions. The slide we wanted to show the variation across the zones themselves and within the zones. So these box plots show the daily zone of ridership, and the x-axis show for each zone itself. So each zone represents a geographical boundary where there's a service of on-demand transit there. So the point that we take from this slide is that we really have a lot of variation between the zone, but we also have across the zone. And these variations are due to so many different factors. There's no one number for on-demand transit ridership that we can say, oh, that's the expected number of on-demand transit operation. It really varies for so many different reasons, and that's what we are trying to understand. But on average, across the region, we have 365 passengers served daily. It varies by the time of the year. So there was a maximum of 643 passenger trips served across the region. So we also take this further to try to explore and look into the spatial temporal variations for on-demand transit across the region. So each of these maps, the color code represents the on-demand transit trips across the different areas in Durham for the different seasons. So the point that I want to make that we do notice when on-demand transit with the data that we have in winter 2022, we had a lot of white or light colored blue areas in the rural regions of Durham, which shows that there was a little bit lower demand. But as we move forward with time, we do see, fast forward to spring 2023, the slides let me see if I can put a pointer, sorry. This map here, we do see that we have much darker color now in the rural regions. Ridership is increasing for on-demand transit. More people are using it. And in these regions, there's no fixed bus routes, or there's very limited operations of fixed bus routes. So in order to understand all these factors, the differences across the time and space, we try to build different models, panel data models, fixed effects, in between effects models that take into consideration our dependent variable, which is the on-demand transit trips across the 18 months, the average daily trip for each zone. And then our other factors that we try to incorporate in the model are based on the on-demand transit characteristics and supply itself, the local transit characteristics, the fixed bus routes, the regional transit characteristics, where does these connections would go, for example, of the regional operator in Ontario of transit in Southern Ontario, in the GGH area, where do they exist, how on-demand transit connects to the GO, how on-demand transit connects to the local transit systems. We also look into external characteristics like weather, gas prices, socioeconomic characteristics, travel behavior, the built environment of all these different service zones. And we use different data sets, the census, the TDS. We were provided data from Durham for the local transit. We were provided with data from Metrolinx for the regional transit system. And we do a fusion of all these different data sets that exist at different spatial units into what we call the service zone level. So for each zone where on-demand transit operates, we have all these characteristics that we use for the modeling. And how is this approach innovative compared to the studies that exist in the literature? So most of the models in the literature are based on surveys, whether RP surveys or SP surveys. They could be based on a smaller area or one zone of operation or a small town, specific town with on-demand transit that runs door to door. But we are using a trip at a regional level that includes different municipalities, include rural, urban, overnight, day zones. We don't build our models based on the census tracts or the TAZs, but we build our model based on the service zone level itself. We want to imitate in a fixed bus route, we do model things based on the route ridership. So we predict a route itself. But in our case, since we have an area, we don't have a fixed geography. So we try to build to imitate this route kind of prediction into service zone prediction of on-demand transit. And we did not take a pilot project. We took a permanent on-demand transit where it also incorporated changes between on-demand to fixed bus routes. So the demand is more stabilized and we have a better interpretation of that data. So just to move on to the model results, and I want to highlight here that we do see that the socioeconomic attributes of the service zone itself were one of the most influencing factors that affected or increased the on-demand transit ridership. So this is the results based on one of the Planar regression models. We focus on socioeconomic attributes, transportation attributes, and some service characteristics of the on-demand transit service. So we do notice one interesting results that we notice is that the proportion of senior population in a service zone had a significant effect on on-demand transit ridership. And it's something that we don't usually see in conventional transit models, which usually it has a negative effect. We do see that income has a negative correlation, which is something we also expect and something typical with transit demand. We also see that land use, employment, and population have a positive effect, which is also typical for any demand or ridership demand studies. When we move to the transportation attributes, we do notice interesting results compared when we look at the vehicles to household ratio. So like reflecting some car ownership, and it's significant and highly elastic as well. And it's negatively correlated, which means people who are using on-demand transit typically have a lower car ownership, which is also something consistent with the models that we see. For the sake of time, I will move to the service characteristics attributes, which were presented as dummy variables, and their interpretation are a little bit different. So from the model results, we do see that the on-demand transit zones that operate as a first mile, last mile, which connect to the local transit system that operated by Durham increases the on-demand transit ridership by 9%. We also noticed that specific GO connections to the regional transit system also had ridership increases by 40% compared to zones that do not connect to the GO. And finally, we saw that the on-demand transit zones that replaced underperforming bus routes had also 69% more ridership than other zones that did not replace an underperforming bus route that were like in a new development or a new area. So we wanted really to translate all these findings into appropriate outputs and guidelines, and we divided these into how does successful on-demand transit look like in terms of location and time, in terms of service, in terms of area, and in terms of the general characteristics of that area. So just briefly, in terms of time and location, we know where fixed bus route is limited, we can provide on-demand transit. Where fixed bus route is underperforming, we can provide on-demand transit and replacement, or lower travel demand areas like the rural areas in Durham. When we talk about the service itself, connecting to fixed bus routes, whether the local transit system, regional transit systems, has really good impact on that. When we talk about the area characteristics, we look into areas that have higher senior population, lower income, higher population of visible minorities, and areas with lower car ownership with respect to household size to be adequate candidates for on-demand transit zone, for on-demand transit. And finally, on the general characteristics, the land use, the employment, and the population. I just want to conclude with the ongoing work that we have been also extending, which looking into the cancellations of on-demand transit. So unlike the private on-demand transit companies or like the ride-hailing companies, users of on-demand transit don't pay for the trip when they book it. They pay when they board the bus. So there's no penalty for cancellations, and it's hard to put penalty for those users that use a public service. And we noticed from the data that there's a high rate of cancellations in the case of Durham region. And that's what we are trying to model as in our next part of this project, is to understand or predict the probability of a trip to be canceled based on the trip characteristics and based on rider characteristics in order to really help minimize operational costs. How can we improve dispatch policy? And look further into those canceled trips when they are canceled and what's the risk associated with each cancellations. We notice some cancellations happen really like very long, a lot of hours before the scheduled trip time. So these don't have the same cost impact on the operation as the high risk cancellations that people no shows or canceling the last minute when the bus is already dispatched or waiting. So we do have this distinction, and we try to predict what's the risk associated with each cancellation further. So with that, thank you, and I'll be happy. I'll thank the Regional Municipality of Durham to provide us with on-demand transit, their trip data, and their continuous support throughout and answering our questions. And I will take your questions.
Well, thank you very much, Ala. So the first question is there any demand prediction model and fleet size calculation for on-demand transit application for a particular area? And that's at the planning level.
So in the literature, we didn't see at the service zone level. We did see more of the predictions at census tract or TAS level, but not at a certain, let's say, zone level, which when this prediction at the census or the TAS level, it's hard because you don't define a certain zone, you don't define a certain operation, so it's hard to do the fleet prediction. But that's what's common in the literature.
Okay. Any other questions to Ala? So, Ala, if you can just talk a little bit about the distinction between urban and rural. In terms of the operation, I think you mentioned it quickly, but if you can just elaborate a little bit more about the distinction between urban on-demand transit operation and demand versus rural.
Yeah, so the urban on-demand transit mainly operates to fill gaps in the fixed bus route transit systems to connect neighborhoods that have long waiting time, have a long walking time to access fixed bus routes or areas where there's no fixed bus routes. So it really focuses on filling gaps where fixed bus routes is not accessible or it's not there or there's low coverage. But when we look on the rural areas of Durham, Durham started this to provide service for the rural areas where a fixed bus route doesn't make sense because of the demand is so dispersed, demand is low, and it would be really costly to operate fixed bus routes. It's really big, and the rural part of Durham is huge, and on-demand transit was a good solution to provide the service, and it mostly operates door to door or curb to curb in those areas. I hope I answered your question, Amr.
Yes, yeah, thank you. There's a comment and a question by Brendan. So some of your variables are only available at TAS census level, example, seniors, socioeconomic, etc. How can you match those to the service area?
Yeah, so we did use GIS to do the spatial fusion, and especially also the census tract, the areas that are present at the dissemination area. So we did use some aerial approximation and certain tools in GIS to do the spatial fusion and to predict what the average, let's say, characteristics of a certain area based on how much TAZs are within that area or how much TAZs this area process or incorporate.
Good. Yeah. Okay, good. Okay, thank you very much, Ala. So we move now to the next presentation. So as I mentioned, Ala's presentation and the next two will be focused on on-demand transit. So one important step really in um, redesigning a transit network and looking for opportunities to consider on-demand transit is really one important step is to analyze the system, the performance of the system, especially with respect to some of the factors that Ala had identified in her research. So this is what the next presentation is going to focus on. So it will be delivered by Dr. Diego da Silva, who's a mobility network postdoctoral fellow at the Transit Analytics Lab. So Diego has been with us for a number of years, contributed to several projects. He specializes in computer science and AI for public transportation modeling. And some of his projects include studying how to recover subway ridership in Toronto after the pandemic, electric buses, analyzing subway incidents, and creating OD matrices. Now, Diego is extending the modeling of the transit network design problem to include on-demand transit. So, Diego,
Hello.
over to you.
Can you hear me?
Yes, we can. Go ahead.
Can you see my screen as well?
Yes, we can see your screen. Go ahead.
Okay, thank you. So good morning, everyone. So today I'm excited to talk about the essential role of transit network redesign in creating more sustainable, efficient, and accessible urban transit systems. Just a minute. Okay. To start, let's define network redesign. So network redesign is the process of updating or restructuring transit routes, services, and connections within a city or region. So this redesign isn't about just adjusting bus routes or tweaking bus schedules. It's a comprehensive rethink of how transit serves our communities, often with an emphasis on modern needs and mid to long-term goals. So we can say that public transit is at a pivotal moment right now. So because many cities are facing now issues like shifting travel patterns, the rise of remote work, and new technologies. So all challenging traditional transit models. So there's a clear need to adapt, not only to improve operational efficiency, but to ensure that transit networks remain relevant, accessible, cost-effective, and resilient. So today I'll walk through the main reasons why redesigning transit networks is crucial, touch on the benefits, and discuss core principles for effective redesign and share an example at the end. Let's begin by examining some of the significant challenges facing transit networks today. So first, demographic shifts. So cities worldwide are experiencing rapid population growth.
Diego, sorry to interrupt you, but we still see the first slide, the title slide.
Oh.
Yeah, now we see the second slide. Yeah.
Okay, thank you. Which slide do you see now? Is the current challenges in transit networks?
Yeah, yes, this is the slide we see.
Okay, thank you. Okay, so first, demographic shifts. As I mentioned, so cities worldwide are experiencing rapid population growth, changing age demographics, and urbanization trends that impact transit demand. So seniors, for example, often rely heavily on public transit and may require accessible routes that minimize transfers and long walk times, as mentioned by Ala in her presentation. So next, changing travel patterns. So remote work has become more prevalent. So meaning that traditional morning and evening rush hours no longer capture the full scope of transit demand. So suburban areas have seen more growth as people move farther from city centers, creating new demand for cross-regional transit routes rather than simply commuting to downtown. So I recommend Roger Chan's presentation on this topic this afternoon. Another major factor is technology and innovation. Shared mobility options like ride sharing and microtransit have transformed how people move around cities. So this has increased competition for public transit and emphasized the need for integration with these new modes to provide a seamless travel experience. As mentioned in the previous presentation, on-demand transit is also an attractive alternative for some cities, primarily to address gaps in service or accessibility within the system. So in this presentation, we will focus more on ODT, on-demand transit, and how to integrate it in the planning stage. So finally, environmental concerns are pressuring transit agencies to improve services and reduce the need for car travel. So transit network redesign can encourage people to switch from cars to public transit, lowering overall emissions. So these challenges make it clear that redesigning transit networks is not only beneficial, but necessary. Next slide. Okay. So now let's look at the benefits of transit network redesigning, how it addresses the challenges we just discussed. Can you see the slide?
No, still the current challenges.
Yeah, so I think there's a delay. Can you see now?
No, not yet.
Yeah.
No, not yet. Yeah, it's good now.
Okay. Can you see now?
Yeah, but we see the key principles, not
Okay.
the benefits.
Okay. Sorry, I think there's a delay from my side. Okay, can you see now the benefits?
No, yes, now we see it.
Sorry, I think there's a delay from my side, but let's see if we can manage this. So now let's look at the benefits of transit network redesigning, how it addresses the challenges we just discussed. So one significant benefit is efficiency and reliability. So redesigning transit networks allows agencies to streamline routes, focusing on high demand corridors, and reducing underused routes. So this approach improves on-time performance as transit vehicles face fewer bottlenecks and reduce wait times for passengers. Another key benefit is increased accessibility. By connecting underserved neighborhood to major job centers, the schools, and healthcare facilities, redesign networks and improve the quality of life and economic mobility for many residents. With an intentional focus on inclusivity, redesigns ensure that transit isn't just convenient, but accessible to all. And sustainability is also another critical advantage. So redesigned networks can support environmental goals by reducing car dependency. Additionally, cost effectiveness plays a significant role by focusing resources on rare areas or highest demand and removing redundant, low-performing routes. So transit can do more with less. So this not only makes operations more sustainable in the long term, but also improves service quality for the most critical routes. So this presents a great opportunity for on-demand transit to enhance the overall goals of transit systems by targeting specific markets, such as certain areas or routes where fixed route transit is less effective. I'm switching the slide. Just let me know if you can see the next slide. Still
not there.
Yeah, there's a delay here. Can you see?
No, it's a bit slow.
Yeah. I think it's from. Okay, still, let's move on to the presentation. So I will talk about the key principles of effective redesign. Okay. So first, data-driven planning is essential. So today's technology allows us to leverage vast amount of data on travel demand, commuter behavior, and peak usage patterns. So predictive analytics can help forecast future needs, allowing agencies to proactively adjust routes and services. So next is stakeholder engagement. So a successful redesign doesn't happen in isolation. So by involving local communities, government agencies, private partners, and transit operators in the planning process, we ensure that the final design aligns with the needs and priorities of those you serve. So flexible and resilient design is another core principle. As we've seen, demographics and travel patterns are always shifting. So it's essential to create a network that can evolve over time. So this may mean designing routes with scalability in mind, or developing policies that allow for quick adjustments based on real-time data. And finally, equity and inclusion should be prioritized. So redesigns need to consider the needs of disadvantaged or low-income communities who often depend on public transit the most. So by providing these communities with access to reliable transit options, we promote inclusivity and improve overall quality of life. I switch it again.
Diego, do you prefer that we run the backup presentation we have? Okay.
Yeah, I think so. If you can, maybe it's better.
Yeah.
So I will stop sharing here mine, and then you can.
Okay. Yeah. Karim, can you just show the copy that you have?
Yeah, I will share now.
There's a delay here on my side.
Can you see it?
Yeah.
Yeah.
Okay, go to slide 6. 6. Yeah, thank you. Thank you so much. Okay, so in the shift from traditional design paradigm to redesign paradigm, a crucial opportunity arises to leverage on-demand transit as a flexible, responsive solution in the transit network. Relies on fixed routes, and actually, as you can see in the framework, we have more interactions between these boxes of the flow charts. So this means that we need to integrate fine-grained data and user demand into service planning. So this is like the traditional, let's say, the classical way to plan a transit network, but usually is more in the sequential steps. So we start from need assessment and goal setting, and then data collection, supply, demand, and assessment outcomes. Here we have more interaction between those boxes and the boxes, for example, from supply, demand, and assessment outcomes. So ODT can replace low utilization routes, reallocating resources toward high demand areas and optimize efficiency without sacrificing service quality. So these are the core principles that we can use when we are designing here the ODT, including in the planning stage. So in areas with inadequate transit access where fixed route services may not be feasible, ODT options can fill gaps, providing residents with a reliable connection to essential destinations. So this approach allows transit agencies to address equity imbalances, especially in equity-deserving regions that might have historically been overlooked due to lower ridership volumes. So next slide. Okay, so to illustrate the real-world impact of redesign, let's look at an example of analysis we did recently for My Way. So the transit agency in Mississauga, Ontario. So the maps provide a picture of coverage and access to job opportunities. So coverage in the left, job opportunities, access to in the right. So they show two essential stories, one where services are unavailable and another highlighting the interaction between transit service and land use patterns. So these maps were made using data sets provided by My Way, and the whole analysis helped us illustrate trends throughout the day and across different seasons, and also to identify the spots that we should focus when you're defining the candidates for ODT zones. So usually for access analysis, we build maps at an interval of 15, 30, 45, and 60 minutes. In this case, the map on the far right points out which areas have the most limited access to job opportunities when we look specifically at the difference between 45 and 60 minutes of travel. Because if you can compare here the two maps, we have 45 and 60 minutes, so we don't see many changes on 45 minutes access. 60 minutes, we see the color changing here, so we calculate the difference and see if we increase 15 minutes on the travel time, what are the areas or what are the regions that we don't see any change. So these are the areas that we should pay more attention. So next slide, please. Okay. Let me change mine here. So this slide connects demographic data to the most relevant factors in implementing ODT as highlighted in last work. So this data helps to identify not only equity deserving areas, but also potential demand. And this is important because ODT can also serve as a catalyst for new ridership. So you can use ODT not only to replace low utilization routes, but also, or even serve equity deserving areas, but also to if the city is planning or is planning to develop some new region, and we know upfront that region will generate more demand, then we can also use ODT as an initial step before implementing the fixed route transit. Okay, next slide. Okay, so another essential analysis is utilization. So to illustrate the analysis, we know that buses carry a certain number of seats, and the aim is for this capacity to be used to the maximum throughout the route. So of course, while complying with service and safety standards. So for each segment S traveled on the route, we have a volume of passengers boarding and alighting, and generating the curve illustrated in the graph. So bus capacity C, as you can see on top, and DL represents the departure load for each segment S, and S is the length of the segment. Okay, next slide. Okay, so when we compare the utility capacity of the vehicle versus the departure load in each segment, we get a value that we call alpha in this graph. So the segment with the maximum value is called the maximum load factor, or alpha max. So when we calculate the area in green for all segments regarding the yellow area, we get the average load factor, or alpha average, for the entire route in one direction. Okay, so we have these two values, one to estimate the load factor for the entire route, and the other one to identify the segments that is more crowded or have more boarding and alightings in the route. Next slide. Okay. So with the maximum load factor and average load factor, we can create a graph that tells us the performance of the routes. And each letter indicates in this chart A, B, C, D, F. So A is high performance portion with high maximum load factor and high average load factor, while B is the lowest performance box. So the dashed line at 0.8 and 0.2 can be defined by the transit agencies. In this case, we follow the My Way service standards. So just to interpret how can we understand like this chart, a maximum load factor of less than 0.2 indicates that the segment with the maximum load factor is less than 20% of the vehicle's capacity at that particular segment, while the average load factor below 0.2 indicates that the weighted average departure load over the length of the segment is less than 20% of the capacity per unit distance. Okay, so next slide. Okay, so we can see how to visualize this data and how the routes behave differently in terms of performance when we compare weekend versus weekday, and also throughout the day when we contrast early morning and AM peak, midday, PM peak, and late evening. So the colors are the subcategories that help us identify the type of route. So each data point is a route. So we average, in this case, for the winter season, and each color encodes the type of service for that particular route. If it's a residential, employment, circulator, shuttle, school extra, or express. And we can color code the frequency as well. It's not in this chart, but we have some examples that instead of the categories of the routes, we can split into low frequency, high frequency. And we can observe, for example, if we have any high frequency route in the low performance quadrant. Next. Okay, as a result of this analysis, we can plot utilization maps and identify subsets of routes with low utilization. So in the example, we can see there are 6 clusters. So together with the coverage, demographics, and accessibility analysis, these clusters will form the candidates for on-demand transit zones. Obviously, we must consider costs as well for a more detailed analysis. But I think this, from a technical perspective, we have some good candidates to drill down. Next slide. Yeah, in the case of Mississauga, we can also create profiles for each low utilization route and understand the proportion of users categories that use that particular route. So here we can see the percentage of child, student, senior, and adult. So this data we extracted from the AFC data set. So for each route, we can design and derive this profiles to understand the patterns and the characteristics of each route. Okay, next. Okay, and finally, we could also visualize demand in both directions. So this data will help us to understand the current demand and possibly be used as an input in the modeling phase of the ODT service. So if you are planning to replace the route, it's important to understand the demand because this will impact costs and the number of vehicles that we will implement in each zone, the type of service, and in conjunction with the data that drill down the characteristics of this demand, then we can design which is the best service for that particular zone. Next. Okay, so in conclusion, public transit network redesign is essential to create efficient, resilient, and accessible transit systems. So transit network redesign should consider ODT as a viable option. Not only can ODT be the one of the answers to a more flexible transit network, it can also be used as a catalyst for new transit demand. So more sophisticated performance analysis methods, such as EAA, can be applied for a more detailed diagnosis. So this topic will be covered by Reza in the next presentation. And lastly, I encourage all of us to continue advocating for research, collaboration, and innovation in transit network redesign. So a huge thank you for the team, My Way team. They helped a lot sharing the data and also answered the questions we had during this process. And thank you. I'm open for questions.
Great. Thank you very much, Diego. If anyone is interested or have questions for Diego, you can put them in the chat box. So one question is, for My Way routes deemed acceptable for on-demand conversion, are there periods of the day where current demand exceeds on-demand transit capacity? That's a question to you, Diego.
Yeah, so it's a good question. So yes, there are some periods of the day that the demand exceeds ODT capacity. So that's why I think right now this is the planning stage. So we are still trying to understand and profile the whole region. And the next step is the modeling stage, which will be, we will address this kind of questions. So for example, if we have a higher demand, what kind of service, as Allah's presentation was pointed out, we can design the on-demand transit service different, like in multiple ways. So we try to identify which service is the best for that particular region, for that particular topology, demand, or destinations. So yeah, so to address this question in the modeling step, so we need to consider all of this. But as I said, in this initial phase, we identify some routes that they have a potential, how can I say, the current demand exceeds like the average ODT capacity.
Yeah. Maybe just to add to this, this is part of the work that also Ala has alluded to now. She's looking into cancellation behavior. So some of the cancellation is actually happening because of a surge in demand that exceeds the existing on-demand vehicle capacity. So understanding this behavior, of course, it's really a stochastic process. The demand is not really stable demand. It really varies over time. It's a stochastic process, as well as the service availability, the on-demand transit vehicle availability also is subject to some uncertainties and some stochastic elements in the system. So the interaction between both the stochastic demand and the stochastic vehicle availability is, part of the ongoing work now that we're looking at. Then becomes the following question would be then, okay, given the pattern of variations in both demand and service, what would be a good level of service or a good vehicle capacity, fleet capacity that would be needed such that we achieve, for example, a minimum cancellation rate from the side of the service provider. So this is something we haven't really reached that point yet, but it's in the horizon. It's part of our research portfolio. Okay, any other questions to Diego? I think we're running a little bit behind schedule, so let's move to the last presentation. So Reza will be delivering the last presentation. He's a postdoctoral fellow at the Transit Analytics Lab, and his current research focuses on public transit network design, hybrid fixed route, and on-demand transit network redesign. Aside from research, he likes hiking, cooking Persian and Turkish foods, and playing FIFA 24, which is a video game for those who don't know. Okay, Reza, so over to you.
Thank you, Professor Shalabi, for the introduction, and good morning, everyone. My name is Reza Mahmoudi, and I'm going to present another ongoing project in Transit Analytics Lab related to on-demand transit service, which is titled To Fix or To Flex, the optimizing inefficient fixed route transit or shifting to on-demand for greater efficiency. A group of 4, including myself, Dr. Diego da Silva, Professor Amar Shalabi, all from University of Toronto, and Professor Kerstens from IESEG School of Management in France, is working on this project. As I mentioned, this is an ongoing project, and today I'm just going to show you what is the considered problem, what kind of methodologies we are using to deal with that problem, and what we have achieved so far. Let's remind ourselves again, there are 2 major motivations to implement on-demand transit service within a city. Introducing transit service to uncovered areas or replacing inefficient fixed route transit with on-demand transit services. If the objective is the second one, step 0 will be evaluating the performance of existing transit network and identifying inefficient transit routes and segments. To this end, traditionally, transit agencies use a set of KPIs to evaluate performance of transit routes from different perspectives. But there is a challenge with this method, which is how to aggregate results of different KPIs for a single transit route. A commonly used approach is obtaining efficiency scores based on the results of multiple KPIs, which is called the absolute efficiency score, which transit agencies obtain this score by calculating weighted sum of outputs divided by weighted sum of inputs. We call it absolute efficiency efficiency score because to evaluate the performance of a transit route, they just focus on the performance of that specific transit route. But there's a limitation with this assumption because using absolute efficiency scores, we can label multiple transit routes as efficient transit route, while some of them outperform other efficient transit routes, meaning that we are labeling some transit routes as efficient transit routes while they are not efficient. Another limitation with just using KPIs is ignoring impacts of external factors like demographics, that we know that these factors affect the performance of transit network and we should consider them for future planning. Also, we say that it's not a good idea just to make plan based on single period performance analysis, because single period performance analysis won't give us the opportunity to understand the reasons for temporal performance fluctuations in the transit network. Looking at the literature and even in the practice, we see that a majority of cases conduct the evaluation in route level. But we claim that we should take this analysis to transit segment level, especially when we try to find the source of inefficiencies in transit network. And when we are trying to find the best strategies to improve the performance of inefficient transit routes, we try to find the answer for this question. If we have inefficient transit route, what is the best strategy? Re-optimizing inefficient fixed route transit services or shifting to on-demand transit services? If the answer is shifting to on-demand transit services, should we fully replace an inefficient transit route with on-demand transit service, or should we partially replace this inefficient transit route with on-demand transit services? And in order to answer this question, we need to take our analysis to segment level. So in this project, we are developing a tool which integrates multiple methodologies and follows an interactive process with transit agency in order to evaluate the performance of transit routes in a specific city, identify inefficient transit routes, inefficient transit segments, the source of inefficiencies, and finally to provide best strategies to deal with source of inefficiencies. And to do so, we consider addressing all of these gaps and issues that I mentioned in previous slides. So let's start with methodology. Data envelopment analysis is one of the methodologies that we have included in our tool. Let's focus on the city of Mississauga, which is our case, and assume that we have a transit route, and the transit agency wants to evaluate the performance of these transit routes. Traditionally, they will consider a set of KPIs to evaluate the performance of this transit route. But DEA follows a different process to evaluate the performance of transit route, which makes it an perfect option for the purpose of our study. DEA actually conducts a relative performance evaluation. First of all, it assumes that each transit route is like a system. It takes inputs and produce outputs. Inputs are kind of costs in the system, and outputs are kind of benefits in our system. So it divides KPIs to two different categories, inputs and outputs. Then, in order to evaluate the performance of a single transit route, in addition to its performance, it considers the performance of all other transit routes. And this is why we call it relative performance evaluation. So using DEA addresses many concerns that we had about absolute efficiency score and about aggregating results of different KPIs. But we mentioned that the objective of our study is not just identifying efficient and inefficient transit routes. We want to know the exact source of inefficiencies for every single transit route and transit segment. So we are using a Slack-based DA model, SBM, which is a perfect option to first of all to identify efficient and inefficient transit routes and segments, and then identify the source of inefficiencies in the form of surplus and slack values for our inputs and outputs, and to identify best strategies to deal with these source of inefficiencies. Our tool conducts a multi-period performance evaluation. It runs SPM for all considered operation periods, and it uses Malmquist productivity index to aggregate the results of this multi-period performance evaluation. Malmquist productivity index is a widely used method to evaluate the productivity change over time by decomposing productivity change into two components: efficiency change and technical change. We also capture the impacts of external factors on the performance of transit routes by using Tobit regression analysis. We use this specific model because it has been already proved by the literature that this model performs other alternative methods in the same concept. And this part of our tool considers efficiency score of each transit route and segment as a dependent variable, and it considers external factors as independent variables. Let me give you more details about our approach by explaining its application to our case study, which is City of Mississauga. City of Mississauga is a medium-sized city in Greater Toronto area. MyWay, the transit agency of Mississauga, is running 55 transit routes within the city. Some of them are express routes, while others are local core or local residential or employment circulator or shuttle routes. MyWay is planning to introduce ODT to its transit network, and we are helping them with evaluating the performance of existing transit networks and identifying candidate zones to implement ODT services. As I mentioned before, our tool follows an interactive process with the transit agency. For any evaluation purpose, first step is to identify the list of KPIs or criteria, or in our concept, inputs or outputs. To this end, first, we review the literature. We identify all used criteria in the literature, and also we reviewed MyBase service standards. We prepared an initial list of candidate criteria to be considered in our evaluation. We had a meeting with MyBay. We explained the process, the problem model, and we shared the criteria, the list of the criteria with them, and asked them to shorten the list. Then we reviewed their list to see if there is any missing criterion, and we updated the list, and we continue and we shared it with MyWay and asked their feedbacks, and we continued this iterative process until reaching the final list of inputs and outputs for our analysis. And the second step, since we claim that we should take our analysis from route level to segment level as well, next step is to identify segments for each transit route. The easiest way is to consider the distance between two consecutive stops on each bus route as a segment. But there is some issues with this assumption. First of all, in most cases, the distance between two consecutive stops are very short, making it meaningless to conduct performance analysis. Second of all, some of routes, they are very short to be divided to multiple segments. And also, another issue with this assumption is that we should note that not all of stops are suitable location to be a terminal for a new transit route. So we explained this process to MyWay, and we asked them to divide their transit routes to multiple segments. And next step was to identify external factors. We identify a list of external factors based on previous studies, analysis studies, and the studies that we are currently doing, literature, etc. And we shared this list with MyWay and asked their feedbacks. And again, we do this process until reaching the final list of external factors. Having the external factors, the list of segments for each transit routes, and list of inputs and outputs, we run our tool to evaluate the performance of transit routes and transit segments in multiple periods, and we map the results in order to provide exact strategies, optimal strategies to deal with the inefficiency sources in both segment and route levels. So we completed the first step. We finalized the list of inputs and outputs for our analysis. We ended up with 7 inputs and 5 outputs. In the second step, which was segmenting transit routes, Actually, we received a very smart suggestion from MyWay. They suggested to consider timing points on each transit route to divide those routes to multiple segments. For example, you see the results for segmenting route number 14 in the city of Mississauga. Since it has just one timing point, we have divided this route to two different segments. So we evaluate the performance of each segment separately. We identify if they are efficient or inefficient. If they are inefficient, what are the source of inefficiencies, and what are the best strategies to deal with this source of inefficiencies in each segment. We are doing this analysis for 20 different operation periods from January 2023 to August 2024. The interactive process that I explained, it's taking a long time, especially when it comes to prepare data for each operation period. So far, we just have clean data for 3 months, January, February, and May 2024, and they are all just in root level. So I'm going just to share some of our findings based on these 3 evaluation periods. So our tool, before being executed to evaluate the performance of transit routes and transit segments, checks the correlation between selected inputs and outputs. If for any pair of inputs or any pair of outputs, and this correlation is high, it removes one of them and keeps another one in order to not repeat any criteria. We did this analysis, correlation analysis, for our case, and we found that there is not that much high level of correlation between any pair of inputs and outputs. So we kept all of identify inputs and outputs in our analysis. We run the first step of our tool, the SPM model, to evaluate the performance of transit routes within the city of Mississauga in 3 different operation periods, January, February, and May. And we find efficient and inefficient transit routes. Here, I just shared the results for 5 selected routes, route number 1, 2, 3, 4, and 5. First of all, obviously, we see that there is fluctuations in the performance of transit routes over time. So we need to consider these fluctuations in our analysis, and we need to conduct a multi-period performance analysis. Second, let's focus on route number 1 and route number 4, which are interesting cases. You can see the location of these routes on the map in right side of my slide. So for route number 1, we see that it was inefficient in January and February. Even we see a decreased efficiency score from January to February. But all of a sudden, it becomes a fully efficient transit route in May. But for route number 4, it was always inefficient. However, we see that in February, the efficiency score for this route has been almost doubled compared to January. But again, we see a decrease in its performance in May. We can analyze the reasons for these changes using the results of Marcus index. So, for example, let's focus on the results of Marcus index in months of January and February. Looking at route 1, we see that remember, we observed a reduced efficiency score for route number 1 from January to February. We see that the reasons for this decreased performance are negative changes in efficiency and technological side of this transit route. But looking at route number 4, it was inefficient in all 3 operation periods, but the performance score for this route was doubled in February compared to January. Looking at the results of Marcus index, we see that the reason for this improved performance was the huge positive efficiency change in the performance of this network. It means that there was not any technological change in this route. Everything that happened to improve this performance was related to how we operate this transit route in May compared to how we was operating it in January. The same analysis can be conducted for every single transit route and transit segment in all operation periods. As I mentioned before, In addition to identifying efficient and inefficient transit routes and segments, our approach identifies the source of inefficiencies. For example, here I show the results of our SPM model for route number 1 and route number 4 for 3 different operation periods. Let's just focus on the results for route number 1 in operation period of January. So efficiency score for this route was 0.74. Looking at the slack and surplus values, which are reflecting the source of inefficiencies, we see that some of inputs and outputs don't have any slack values. It means that actually this route is performing pretty well from the perspective of those inputs and outputs. But if we have positive values, slack and surplus values for other inputs and outputs, it means that we need to make some improvements from these perspectives. For example, we see that the slack value for load factor is 0.24, or for cost recovery is 0.13. It means that in order to make this transit route an efficient transit route, one strategy is to improve cost recovery up to 0.13 percentage. Or we see that we have additional stops on this transit route, making it maybe pretty slow and unattractive for transit users. But how we should improve the performance of this transit route? We should look at the reference sets. For reference set of route number 1, in January, we have route number 11, 1939. It means these routes are fully efficient transit routes in January, which have highest level of similarity to route number 1. So the transit agency should look at these routes to see what they are doing in these routes, and they are not doing in route number 1 in order to improve the performance of transit route number 1. The same analysis can be conducted for all transit routes and transit segments in all the operation periods. We also can map transit network.
Yeah, Reza, sorry to interrupt, but we're running short of time, so if you can conclude as quickly as possible.
Additional slides. Yes, sorry. We can also map the transit network based on efficiency scores. So here I have just mapped the transit network based on the efficiency scores of January. Looking at this map, we can see that there are some zones within the city that all fixed transit services are inefficient in those zones. Actually, this finding suggests considering the possibility of replacing fixed route transit services within these zones with on-demand transit services. So as I mentioned, this is an ongoing project. So for the next steps, we should prepare all required data for all the operation periods. Then we will run our tool in both route and segment levels. We will use creative approaches to map our results. In addition to this analysis, we will consider on-demand transit cost recovery estimates and equity requirements in order to optimally answer the question of to fix or to flex. Thank you for your attention.
Thank you, Reza. Very interesting. We have one question, and that's actually the time we have left. So can you explain what defines technological change? How can it vary month by month? If you can just...
Yes, so technological... Is it technological? Yeah, technological change reflects actually the changes in the technology side of transit network. For example, if comparing to like February to January, if we have introduced new electric buses, more full efficient buses, or any technology related to our transit network, which makes it more cost efficient, more attractive for our transit services. How can it vary month by month? So as I mentioned, we can introduce a new technology, say, for example, in February, which affects the performance of our transit network compared to January.
Okay. Yeah, we're running actually a little bit late, so I think I'm gonna bring it to a close here. Well, thank you very much to all speakers. We're going to have a 15-minute break now, and then the next session will start at 11. So please make sure to join back at 11, and we have a set of very interesting presentations coming up. Okay, thank you, and we'll see you shortly.